Welcome to Git Distilled. As software developers, we use Git all the time. Let us step back and look at it from another view. What does Git stand for? There is a lot of debate. I would say Global Information Tracker. It was first released in 2005, created by Linus Torvalds, who is also credited with Linux. The design goals were: number one, it should be reliable. The content that you put in should be the content that you get out of the Git. It should detect corruption and prevent any mutation of the data. Uh, Highly reliable systems also have simple design, and that's what Git also does. The Git is also supposed to be highly performant. Today we have thousands of parallel branches that people create, and Git excels at creation of branches and merging of branches. It is able to handle very large projects. In many companies, monorepos are hosted on Git. Git is also an example of distributed system. So no, there are no single points of failures. There are no servers that if they go down, the content would be lost. And that also brings us to another point, which is that there is no node that is special. Every copy of Git repo has all the information, and you can easily get back things. So there is no lot of times in open source there is no need to even back up your repo, because you can always get back that repo from a mirror or somebody who has forked or cloned it. The design goals are not ordered as per the importance. In fact, all of these are important. If you had a system that was not reliable, it would corrupt your data, or it would take forever to do things, or it wasn't distributed, I don't think it would be as popular as what Git has become. So the way to think about Git is that there is a giant graph. Okay, so first at the repo level, right, you have a repo in the cloud. Many people fork out of it, they create their own repos, and people can fork out of the fork of the repo, and so on. So there is a network of repos, and these repos get cloned. So when a developer works, they clone a repo on their laptop, and in fact you can clone from a repo on the laptop, and you can create two clones. Usually not a good idea, but you could do that. And you could also clone between different repos on different laptops, provided you have a Git SSH server running. Inside a particular repo, you have a network of commits. So these are all commits, and as we see that usually there is a main branch which is also called as master, and you branch out of it, and sometimes you branch and merge back into it. So ideally the idea is that you branch, do your work, and merge back into one of the shared branches. So there is a huge network of repos, which repos pointing to each other, and inside repos you have branches, and branches pointing to each other using commits. One of the benefit of distribution is that it supports offline case very nicely. So let's say you cloned a repo from GitHub on your laptop, and then you went on a plane, you added code, you created branches, and you committed to your local repo, all without needing any connection with the main repo. And once you come back to the network, you would go and sync up your repository with the main repo. So you would either push your changes, or if there is a if the main repo has been modified, you would pull it first, rebase it, and then push it again. The core idea is that when you took a copy of the repo, when you cloned it, or you did a pull, right, the changes that you saw, or the history that you had, that history will not change on the server. So if you add something, then Git will take that addition and push it onto the repo, and vice versa. If there are some additions done on the main repo, those come back. But what the history that existed when the pull or a clone was done, that history doesn't mutate. And that has huge benefit, because next time you do a pull, you don't have to get the whole thing. You just need to know the last point at which you pulled, and you give that commit hash, and only the delta that is needed comes to your client. So it saves a lot of network communication. There is also some kind of similarity with blockchain, although they are two very different technologies. But if we want to compare it just for better understanding, in the world of Git, we talk about repo. In the world of blockchain, we talk about ledger. A repo is basically a series of commits, and with branches as well. Blockchain is a series of blocks. Each commit has an address, which is a SHA, and block also has a SHA address. These are arranged as Merkle trees. In the world of Git, you use network of trust to merge changes. So when the changes are coming in and you want to merge to a common branch, a master, you would use a network of trust. Uh, some people will be allowed and some may not be, etc. In the world of blockchain, the trust is established based on proof of work, and there are other kinds of proofs, but there is some kind of trust uh, mechanism in blockchain also. So they are similar in some ways. They both maintain history, and the history is not changed, and you can keep adding to it, keep mutating the content, but the history keeps adding, and you don't history doesn't change retrospectively. Git internally is modeling a file system and a change tracking mechanism. Contrary to naive thinking, it doesn't keep deltas but the whole file. So Git has two kinds of things, objects and refs. Let's talk about objects first. So what is an object? So think of Git as an content management system which stores different kinds of objects. The most important of those objects is content. For example, if you add a file, the content of the file is getting added to the Git store. The every Git object has a hash. So it has a SHA-1 hash, which is a 40 hex or 20 bytes of address, and this address is the most important thing that Git has, and it is immutable. So once you create this, it stays there. There are other kinds of objects. So there are different kinds of objects in Git are, you have commit, file, and tree. So I talked about file. So you add a file and the content of the file gets added, and a hash is created, and Git records that the type of this content is a file, or it calls it blob. Similarly, you can have folders, and folders can refer to other folders, and folders have files, but they are called as tree in the Git store terminology. So a tree basically can have subtrees and can also point to files. Again, the tree will have a content and it will also have a hash. A commit basically points to a change that you are making. It again has a hash. So the commit will have a content. The content will be the tree that you have added, or the files that you have added, new files, all those, that thing that has been added, and other pieces of information like who's the author adding it and what is the commit message, etc. All that becomes content of the commit. Based on that, a hash is generated. That hash is the address of the commit. Every commit also points to a parent commit, and that's how the whole history is maintained. In these situations of merge, a commit might have two parents, because there may be a three-way merge, and the commit is merging three changes, and you could have two parents. Now, what are refs? So some you need human understandable or human names to refer to commits, right? So these 40 hex or 20 bytes of alphanumeric is not easy to remember. So what we do is we start giving them names. So you would create a branch, and that branch essentially is a pointer to a commit. So you would see a file, a ref, and that ref is nothing but a pointer to a commit. Similarly, head is the current working branch, the current uh, branch that on which you are working, and that again is a pointer to a branch, and that branch again points to a commit hash. So every time people talk about head, branch, etc., it's nothing but a commit. So commit is the most important thing, and every commit has a hash that becomes the most important thing to remember. So let's look at some sample commands. Let's say you add a file in the git store. So you say that this is the content, and you call a command called as git hash objects. Hash object, this is supposed to give you a SHA-1 hash of the content. With -w, you are asking it to add that content into the git store. So it has added that content into the git store, and this is the uh, hash. Now if you look inside git objects directory and try to find out files, you will see that there is this thing that added. The first two characters are used as folder name, and the rest of them are used as the file name, and this is where is the content. An easy way to see the content is to use git cat file minus pretty print, and you will see that you got back the content that was added. Now this is about one file, but if you have a folder which is right now, let's say you're on a master branch, and it has two files and a folder, you would see that they are added into the tree, or if this is actually the contents of a folder. So it basically says that there is a file with this commit hash, the name is this, it's the type is blob, and these are the permissions when you create it on the file system. And same with another file, and then it refers to another folder which is again in the git terms is a tree, and it has its own hash and permissions and a human friendly name. Now let's look at a commit. So let's say you create your commit. You could do it using a low level git command, also called as git plumbing command, and once you do it, you will see that it all again generates a SHA for you. If you try to look for the contents of this SHA, and most of the git commands you don't have to give the full SHA, you can give first few characters as long as it can distinguish. You will see that it has few things. So number one, it has a reference to the folder or the tree where all the content, everything that you committed is part of that. So that is the tree, and it contains information about who's the author, etc., right? And if you have a message, that message also becomes part of the commit. Here is an example, a pictorial example of how different how this same thing plays out. So for example, if you have a master, so usually you have a master branch. That master branch might point to a commit. Then you might have a test branch that also points to a commit, and this was your first commit. So when you did your first commit, it you basically added a file, and that file was added with a particular hash. A folder, that your root folder that refers to that, was also added. In the second commit, you created a new file, and that new file has its hash, and also because you modified the old original file test, you create a version 2 of it, and the hash of it changes. And what Git does, it creates a new tree for that. And the new commit, which has its own hash, refers to that tree by the hash. Then you create a new you create a back directory, and you have a new folder created. So the files test.txt, which whose content has not changed, refers to the same hash. The new.txt file also refers to the same thing, but we have now a new folder back, and that refers to the old folder, right? And you have a new tree, and that's the third commit, and that's what is your master branch. So this basically shows that branches refers to commits, commits refer to trees, trees refers to files or subtrees. Let's look at how Git is tuned for branching and merging. So let's say, there are commits, and there was first commit C0, then C1 was done on top of it, and C2 and C3 and C4. Now at C4, your master is pointing to that, and at this point you create a branch hello world. What happens is the Git would create a ref object, and it will say that that ref object reference it points to commit C4, and it hasn't done any copying of code, or any. It's a very, very lightweight operation. It also points the head to hello world, because now that is the branch you are working on. So head always points to the current branch, and current branch points to the latest commit in that branch that you have uh, you know in the history. Now um, you created a branch. So let's take this example. You created a branch, and you made the changes, and now you want to merge it back. So this is what Git does. It will create a new merge commit. It will take all the changes and apply them with that. Now there can be a couple of situations here. Sometimes all the changes that you have done are on top of the changes that are there on the merge branch. So there is not much, there is no conflict. So what it does is it takes these changes and it applies on top of it, and that's called as fast forward. So it doesn't really need to create a merge commit. It can just move the tip of the old branch to the merge commit. Sometimes there are changes and it has to do a merge. The merge can be without conflict. In that case, it just creates a new merge, and everything happens automatically. And in some rare situations there can be a conflict. That conflict, then the merge person doing the merge has to resolve. And once you make those changes, the merge commit is again created with those changes, and it goes ahead. Slight difference between merge and rebase. So let's say you had a branch, and at a commit B, you created the branch and you made changes EFG, while on the main people continue to make changes, and at some point you go and create a merge. What merge would do is it will create a new merge called as G prime, and it will take the changes in G and the changes that were there till D, and it will merge them, and that's what is the usual merge. But sometimes what you don't want to lose the history, so what you do is you do a rebase. So what you do is you let D be there, and then you apply E, F and G, all of them onto the same branch. So this is the rebasing uh, approach. It is always advised to do rebase, uh, because that keeps the history clean. Git has two kinds of commands, uh, porcelain and plumbing, and the analogy is from your sink, where the interface that you deal with is porcelain, what you see on the top, but behind the scenes there is a lot of plumbing that makes the whole thing work. And Git has a lot of commands which are plumbing commands, and some of them we saw: hash object, read tree, write tree, etc., or cat file. uh, but there are very nice, easy to use commands called as porcelain commands that we generally use. So we usually don't use use the plumbing ones unless we want to understand and look at the workings of Git. We would usually use the porcelain commands. Git has almost 110 commands, and 50 of them are porcelain or user facing. They have CLI completion, etc. Plumbing commands are for core Git internal commands, and there are 60 of them that porcelain commands in turn might be using to actually do the work. There is a nice talk by Linus Torvalds on Git. It's a very old talk, but he gives you the idea of distribution and why it's very important. Thank you for listening. Hope you liked it. If you disagree or if you have suggestions, please feel free to add in comments. Um, I look forward to learning from you.